Welcome to This Explainer. Today, we're cracking open Amon's AI journal to take the Trie data structure from a dry, abstract concept and turn it into your absolute algorithmic superpower. If you want to conquer the most punishing string matching problems, or honestly just understand the actual magic powering modern text prediction, well, you're in the exact right place.
Okay, let's dive into this. Have you ever actually stopped to wonder how your phone finishes your sentences almost instantly? Or how a search bar predicts exactly what you're looking for after typing just a couple of letters? I mean, it feels like magic, right? But under the hood, it's a beautifully structured algorithm working at literal lightning speed to sift through thousands, if not millions, of possibilities.
Enter our hero for today, the Trie. Now, I know what you're thinking. It's spelled like tree, but we pronounce it Trie. Because, computer scientists absolutely love to keep us on our toes. It's also commonly called a prefix tree. Essentially, it's a specialized tree data structure designed specifically to efficiently store and retrieve keys within a massive dataset of strings. It is the absolute backbone for everyday applications like autocomplete engines and real-time spell checkers.
Level 1. Building the foundation. Before we can optimize the world's search engines, we've got to establish the basic structural rules of adding and searching for words. Let's walk before we run.
So let's actually map out these pathways as we insert a few words. If we add the word bad, we create a path straight from a root node down to B, then to A, then to D. Now step 2. Let's add dad. Because dad starts with a D and not a B, it obviously doesn't share a prefix with bad, so it branches out from the root into a completely different path. D, then A, then D. The exact same thing happens in step 3 when we add mad. We create yet another unique path from the root. So we have 3 words and 3 distinct starting branches.
Now, what's really interesting here is where the true power of this structure unlocks. What happens when words share a starting letter? If we insert ABC into our tree, and then we want to insert AB, we don't build a new branch. No way. AB simply travels down the exact same A and B nodes we just created for ABC. We just reuse the existing prefix. This means all words that start with A and B live in the exact same neighborhood, which is incredibly efficient for our memory. When it comes to the actual code, Amon's journal outlines 2 main ways to build this. You've got your traditional route using a formal trinode class, maybe utilizing a default dictionary. But contrast that with the alternative, just using a nested dictionary without a formal class. In this method, nodes are simply replaced by dictionaries, and you mark the end of a word by just adding a hyphen key. Skipping the formal class and just using a nested dictionary is a brilliant insider trick. It actually gives you much cleaner code and, honestly, way better performance when that interview clock is ticking.
And honestly, this is exactly why we love this structure. For basic insertions and searches, our time complexity is just O of n, where n is simply the length of the word we're dealing with. It's incredibly fast, and our space complexity here is essentially O of 1 auxiliary space per operation. So our level 1 foundation, it's rock solid and highly optimized.
Level 2. The Wildcard Challenge. Because let's face it, inputs in the real world are rarely perfect. We're leveling up from standard searches to dealing with missing characters. Imagine a user is typing a word, but they throw in a dot as a placeholder for a letter they just don't know. The new constraint here is that a dot wildcard can be matched with literally any lowercase English letter. So if we search for .ad, it could match bad, dad, or mad. If we search for b ... it could match any 3-letter word starting with B. So the crucial point is how we actually navigate our tree when we hit that dot. We can't just follow one specific letter anymore. We have to use depth-first search, paired with backtracking. When our algorithm is moving down the tree and hits a dot, it must branch out and investigate all 26 possible alphabetical child nodes at that specific level. We have to traverse down every single possible path to see if any of them successfully lead to the remaining letters and ultimately a designated end-of-word node.
Now, while standard words remain lightning fast at O of m time, wildcards introduce a massive cost. In a true worst-case scenario, let's say a user searches with a string composed entirely of dots, and we have a very deep tree. Well, we're forced to multiply our search paths by 26 at every single level. To put that into perspective, that boils the time complexity down to a massive O of m times 26 to the power of n. It is a stark reminder that wildcards require some rigorous backtracking.
Level 3 real-world bosses. Let's move to the next phase and see how this all builds up into complex real-world systems.
Our first boss is the add bold tag and string problem. Basically, you've got a string, and you need to wrap specific substring matches in HTML bold tags.
Doing this with brute force regular expressions, it can be agonizingly slow. But deploying a trie, it vastly speeds up finding those overlapping substrings. Once the trie helps us find the matches incredibly fast, we use a merge intervals technique to combine consecutive tags, dropping our complexity down to a beautiful O of M.
And now for the ultimate test, designing a search autocomplete system. Imagine you're building the back end for a massive search engine. You aren't just searching for a word anymore. You're tracking historical sentences, monitoring exactly how many times they've been typed, and dynamically updating predictions. Every single time a user types a character, you have to instantly return the top 3 historical or hot sentences that match the prefix typed so far.
To pull this off, our algorithm has to follow some incredibly strict priority rules. Step 1, we traverse the trie to match the exact prefix the user has typed. Step 2, we gather the matching historical sentences and sort them by their hot degree, meaning we prioritize the sentences that have been typed the most frequently in the past. Step 3, if 2 sentences happen to have the exact same hot degree, we break the tie by sorting them in ASCII code order. Basically, the alphabetically smaller one appears first.
And this brilliantly illustrates the ultimate optimization hack detailed in Ammon's AI journal. Instead of searching the whole tree every single time a key is pressed, we trade a little space for incredibly better time complexity. We actually store the top 3 most frequent sentences directly on each prefix node. Furthermore, we track our search term and keep a pointer to our last node. This means when a user types the next letter, we don't have to start from the root all over again. We just step one node deeper from exactly where we left off. And if we hit a dead end, a no match flag tells the system to immediately stop searching, saving a ton of resources.
By mastering the trie, we've gone from simple letter matching all the way to building a hyper-efficient, state-tracking autocomplete engine. The pure power of prefix sharing makes it an absolute essential for any developer's toolkit. So, the next time you face a massive data set of strings, ask yourself, are you going to just brute force your way through it, or are you going to build a trie and let the algorithm do the heavy lifting? Open up that editor and put this to work.